Right. Hi, everyone. My name is Peter. Really glad to be here. Really glad to bring the latest buzzword to CPPCon. So this talk is part of a series. Next year, I might give a talk about blockchain with C++. Maybe the year after we do HTML5 with C++. But this year, we'll do deep learning. So if you read the description of my talk, you saw that I generally want to convey both machine learning from the researcher's perspective as well as from the engineering backend perspective. And the body of knowledge I want to cover is quite large, so we need some kind of strategy. And you probably all know the OSI model for networking, which splits the networking stack into various layers. So I've taken the freedom of defining a similar model for machine learning, which we'll use as a guide as we step through the different layers of abstraction of machine learning. And the goal of the whole talk is actually just to show you that machine learning is not this Python thing. It's actually machine learning and C++ can appear in the same sentence. And that's what I'll show you as we go down this stack. So we begin at the task layer. The task layer I define as the level of abstraction where we think in terms of the high-level goal or end goal that we want to achieve with a machine learning system. So we usually define such a task in terms of its input and its output. A very common task might be classification. In classification, we have some data distribution, say a set of images that we want to bin into a finite set of bins, so a finite set of classes, for example, mapping images of animals into a finite set of classes, 100 different kinds of animals. Another kind of task that I've been doing a lot of research with are called generative models. And generative models don't immediately appear useful, but I'll give you an example of how they might be useful. Imagine you're working on an open world game like Skyrim, and you want to generate lots of realistic looking sky. So you don't want the sky to look similar, you want to make it look different in different parts of the world. So what you could do is you could go outside and take 1,000 images of the sky throughout the course of a day. And then you could use a generative model to simply generate more of that sky. Where the important detail is that a generative model will not just copy-paste the input to the output, it will actually generate more of its input with variation. So you could feed in your 1,000 images of the sky, and it will generate infinite, or however many images of the sky you want, and you could tile that over your world and have a very realistic sky. One level below that, if we actually pin a particular task that we want to solve, we'll usually have various model architectures that solve the same machine learning problem. And for the task of generative models, there's one kind of architecture that I like very much that's quite recent. And these are called generative adversarial networks, or GANs for short. And these are actually one of the few machine learning models where I think you could probably walk up to any random person on the street and explain it to them in a high level. And they would probably understand how a system like that could learn from data over time without any of the fancy math behind it. So the way they work is that they have a generator which gets a variable z, which is a vector of, say, 100 values. So imagine an array of 100 floating point values. That's the input. And it massages that and transforms that into an image. So initially, everything is initialized randomly, so that image will be garbage. But then there's a second component called the discriminator. And its task is to take an image and emit a probability of that image being real or fake. So we wanted to emit a high probability for the images from our data distribution, so the images of the sky that we took. And we wanted to emit a low probability for the images that we generate with the generator. So we train the discriminator to optimality, and then the learning comes in where the output of the discriminator from the generated images is used as feedback for the generator to tell it how well or badly it's generating images. So you can imagine the generator being some kind of art counterfeiter who gets a bunch of numbers and uses his imagination to generate an image. And the discriminator is a kind of art critic who tells how realistic or how fake or not fake that image is. And the feedback from the art critic is given to that artist to tell him how to change his strategy to generate more realistic images. And the end goal, or the result of that, is actually that the generator learns to generate really realistic looking images. And I have some examples here. So these faces here, and I hope you can appreciate this to some extent, even though it's quite abstract, but these faces here were generated by taking 100 random floating point numbers and transforming them in some magical ways. And you can see the images themselves are quite realistic. I mean, there are some artifacts. So for example, this guy here has like this black blob. Can you see my mouse? Okay, but the person on the lower left, you can see some artifacts in the faces. But nevertheless, I mean, these are really realistic looking images, given that they were generated from random floating point numbers. And what's also really interesting about these models is that because you have this space of this vector space where you can sample numbers from, you can do really interesting things with that space. So for example, here we can take the images on the very left, and we can find the corresponding vector, the corresponding code for those images, and we can do the same thing for the images on the very right. And then you essentially have 2 points in space, and then you can simply linearly interpolate between those 2 points in space. And you can see that we can actually interpolate between these faces. On the bottom, you can even see how the smile of the person becomes larger as we move from left to right. So we have quite a lot of control about about what images we generate with these models. So that's quite interesting. Now, moving one level below that, we have the layer, for lack of a better name. And the layer is actually very important because that's one of the most important levels of the stack at which researchers communicate with each other. So in a deep neural network, or any kind of neural network, you can think of a layer similar to an optimization pass in a compiler. So in a compiler, you have different optimization passes like function inlining, loop unrolling, constant propagation, that are each kind of standalone functions or transformations that take an input program, produce an output program. And similarly, in a neural network, you have layers which perform some kind of standalone transformation of some input, say an image, and produce some kind of other image that is transformed in an important way. And stacking together those layers leads to some output that we want. For example, for the discriminator, we want to transform the image into a single probability value. So let's zoom into the discriminator here, and we can disassemble it into the layers that make up this discriminator model. And we can see a lot of convolutional layers that I'll go into in a bit, and also a flattened layer, which is more of a utility layer that takes a 2D or 3D image and just flattens it out into a long vector. And also a dense layer, which is what you would usually expect from a neural network, has like an input layer with lots of neurons and an output layer with lots of neurons, and those are connected with weighted edges. But let's look more at the convolutional layer, and later on we'll actually see how to implement that. So I just want to go into the mechanics of convolutions. Convolutions themselves are a very general term from signal processing that generally take 2 signals and combine them in a very special way. But let's just look at the mechanics for now. So we have this very exciting image with 9 grayscale pixels. And because they're grayscale, we can look at them as floating point values between 0 and 1. Right? And so for a convolution, we need another thing, which is a kernel. And a kernel is just another small kind of patch with very important floating point values, which are actually learned by the neural network. So the kernel values are very important. But the act of convolution itself is quite simple. We simply plop this kernel onto the image. And for each configuration of the image and the kernel, we simply do a weighted sum of the values in the kernel and the values in the patch of the image. And we multiply those and sum them up and get a single output value. And then we slide the kernel over by 1 step, or actually the amount by which we slide the kernel is called the stride, so we might want to change that. But again, we just produce a weighted sum, and we do that for every configuration of the image and the kernel. And that's a convolution. And I want to give you an idea of, first of all, in 3D, this looks very similar, just that now we have a depth dimension. So for RGB images, we'd have a red, green, and blue channel, so it's a 3-dimensional volume. But still, we'd have a kernel, and we would just slide it across and produce a weighted sum and a single output pixel for each configuration of the image and the kernel. Now, I want to give you a slight intuition about what these kernels actually do and why they're able to pick up very important information about images. So on the left, you have a kernel that would represent very simply a pattern. So you can imagine if you have a grayscale image and you slide this kernel across the image, at any point where you have a vertical line with high pixel intensity, the output of this weighted sum would be high. So you would essentially, you could say that the kernel activates at this point. Whereas in other parts of the image where you don't have such a vertical pattern, you would get a low value. On the right is a different kind of kernel. I'm wondering if maybe anyone has an idea what that kernel on the right might pick up in an image. Heard some things didn't sound very right. It's actually an edge. So it's quite interesting because it's a very simple kernel, but it picks up something quite interesting. So imagine you have a surface with the same color. Because the pixel on the left is the negative of the one on the right, those same color values will actually cancel out. But there's one point in an image where these values would not be similar, and that is at an edge of some surface, right? If you have a different color on the left than a color on the right, this output value will be non-zero. So this kind of kernel would pick up an edge. And we'll look at actual code to do that later on. Before that, let's move down to the graph layer. The graph layer is very important because it's actually the most essential abstraction we have over a machine learning model from an engineering perspective. So now we've kind of left the domain of the researcher and looking more and more into the engineering. So if we take these last 3 layers here, I'll show you what the graph abstraction means. In the computation graph, we essentially think of very primitive operations such as additions and multiplications, and we connect different operations, which are the nodes of the computation graph, together with the inputs of that operation. and then chain the output of each operation with further nodes, further operations. For example, here, even though the convolution operation itself consists of smaller operations like additions and multiplications, because it's so important, lots of libraries like Intel MKL and other libraries actually have them implemented very efficiently as basic routines, so we can think of it also as a primitive operation. And you can see here this convolution, or conv2d because it's a 2D convolution, takes as input an image, also takes as input weight matrix WC, which is this kernel that I mentioned earlier, and also takes in a variable s, which is the stride by which we slide the kernel. And we would perform this operation, and then the output of the convolution would go further into this other layer I mentioned, which is the flatten operation. The output of that would go into a dense layer, which is essentially just a matrix multiplication. So again, a matrix multiplication is actually a more complex operation, which consists of lots of additions and multiplications. But because it's so simple, we also have it usually as a very basic operation. And again, it takes as input another matrix we multiply with, which is another weight matrix. And then at the end, we have one final output, which is the probability in our case. And so this is a computation graph. It's something very abstract. And because it's so abstract, it's the basis for lots of frameworks is, well, implementation of machine learning models. And one thing we can do at this level of abstraction, for example, is actually solve the scheduling problem. So imagine we have lots of devices, or maybe even multiple machines in a cluster. Then at this level of abstraction, we can think of how to place these operations onto different CPUs or GPUs on a single machine, and maybe even on multiple machines. So that's why this level of abstraction is very important. At this point, we can also talk about something different, which is parallelism. So now we're really getting more into the engineering. There's two kinds of basic parallelism we can achieve with a machine learning model. The first kind is called data parallelism. And it's actually quite straightforward. What we do here is if we have multiple machines, we simply copy-paste our computation graph onto each machine, and then we split our input data into multiple subsets, and we simply evaluate the model for each subset on separate machines. Of course, at the end then, when we have our optimization process and we need to pass back the feedback from the evaluation to the models, we need some kind of synchronization barrier. So we usually have a separate dedicated parameter server in our cluster, which would take the output of each model and do some kind of averaging and pass the feedback back to every single instance of the model on the various machines. The other kind of parallelism is called model parallelism. And in this case, we actually really split the computation graph across different devices, across different machines. And this is different because in this case now, usually we have, for each layer, every input is connected to every output of the next layer. So in this case, because the computational graph is split, we would actually have to do synchronization on every layer of our neural network. And this might seem like more of an overhead, but there are actually various benefits to this kind of parallelism. The first is that if your model is so large that it doesn't even fit on a single machine, then model parallelism is the only way to even parallelize it at all. The other way in which this kind of parallelism is actually interesting is that in the previous case, here, after every evaluation, we have to pass all the weights of our machine learning model to the parameter server. And to give you some rough numbers, a popular machine learning model for image classification is called AlexNet, and it has about 130 million trainable parameters. So that's 130 million floating point values on each machine for each of these model copies. And of course, transmitting that from each machine to the parameter server takes a large amount of time. Whereas in this case here, on each particular layer, we might only have, say, 1 million to 10 million parameters. So the latency of each transmission will actually be lower, even though we have more synchronization points. So these are the kinds of considerations we would have to make if we want to parallelize our model. There's another very important distinction between various computation graphs in various machine learning frameworks that you would encounter out in the wild, and that is between static and dynamic computation graphs. Now, in the static computation graph model, you define your graph once. And what this means for your programming is if you look at this fictional programming language here, which is like half C++, half Python, and a third of Go, then the first thing you should notice is that the matrices have to have fixed static shapes. So you need to define them ahead of time. And the other really important part is that if you imagine this would be an interpreted language, then if the interpreter runs through the line saying d equals s times a plus b, this would not actually produce a value. Instead, d would be a handle to the computation graph representing its value. So that's why we could actually say that this kind of programming is declarative. We're actually not computing anything, we're just describing a graph. Similarly, E would not be an actual matrix, it would just be the computation graph that would lead to the value of that matrix. And what this means is actually two things. The first thing is that we usually cannot use the programming language's native control flow. So you usually have weird things like this if clause operation, because you can't actually use normal control flow. You have to add operations to the computation graph that does the control flow for you. So in this case, you would have this kind of if clause operation, which takes a condition computation graph and then two other computation graphs, and then during the evaluation of the graph would return either the one or the other result. And the other thing that this means is that you usually have some kind of evaluate function, which takes a computation graph and then, for example, distributes it across lots of machines, across lots of devices, and then actually computes the output value. So this is the first time you actually get a real output value. The other kind of graph are dynamic graphs. And if I wouldn't have mentioned the word graph, you wouldn't even think of this as a graph at all. But in this case, the graph is more or less defined by run. This means that the matrices don't have to be fixed size anymore. It also means that we can use the programming language's native control flow. And it means that when the interpreter runs through, if it's an interpreted language, if the interpreter runs through d equals s times a plus b, we get an actual output value. And this also means that we don't have to do any kind of evaluation of the computation graph at the end. The reason why it is a graph is that usually these frameworks have to still trace the output, the inputs to the outputs, mainly because at the end you have to compute some kind of feedback and then use the optimizer's output to update your graph. So you still need some kind of graph structure, just that now it's actually computed at each evaluation of the graph. All right, now moving on to the next layer. The op layer, I would say, is the last level of abstraction before we move into actual code. So the idea of an op is that you would have some kind of abstraction over the implementation of some operation for multiple devices. So imagine you have a CPU and a GPU, then for some kind of operation like the convolution, you would have different implementations for CPU than for a GPU. And the op might be some kind of abstraction over that, where the framework would then use whatever implementation is most efficient for your setup. And here I want to talk more about the algorithms that we usually use for machine learning operations. And this is very much about one thing, which is getting to Bob. So this is Bob. And Bob is the guy who works at Intel or NVIDIA or AMD. And for the past 20 years, Bob has been doing nothing else than optimizing 128 by 128 matrix addition. So Bob is not a lot of fun at parties, but he definitely knows a lot about matrix addition. And I'm actually not joking. I've been told there are guys who really, for the past 20 years, have been optimizing one addition. But my point is that we have these very primitive and often used operations which have been hyper-optimized for a very long time. And so a basic strategy we have in machine learning is that very often we'll want to kind of reduce our operation to something for which we already have one of these efficient solutions. So for example, matrix multiplication. And I'll give you an example of that, going back to convolution. There is a way to actually reduce the convolution problem down to a matrix multiplication and then just hand it over to Bob, who has his efficient implementation in like Intel MKL or another library. So the way we can do this is essentially just by, for each configuration of the image and the kernel, kind of take all the values of the image and just flatten them out into a long row vector like that. And for the next configuration, we can do the same thing. We just flatten it out and just put it into another row of the matrix. One thing you should notice here is that between the first row and the second row, we will actually be sharing 2/3 of the values, which is one consideration. But it actually turns out that because matrix multiplication is so efficient, if we have enough memory, this is actually still a very efficient implementation. But let me just continue. So we would do this for every configuration of the model and of the image and the kernel. And now we have a matrix. So that's the first part. Now we need another matrix. And so what we can do now is also simply flatten out the kernel and put that into a column. And if we have multiple kernels, we can simply do that for all the kernels that we have and put them into the columns. And now we can simply put a cross here, and we have a matrix multiplication. And this is actually very similar for lots and lots of operations where we want to simply reduce them to one of these basic linear algebra operations that we usually have very efficient solutions to. Right. Now moving on to the kernel layer. Here we're actually talking a lot more about implementations. So in general, what a kernel really is an implementation of an operation for a specific device. So if we have both CPUs and GPUs in our system, then we'll have one kernel for the CPU and one kernel for our GPU for the same operation. And so here is one kind of function that we would want a kernel for. This is called a sigmoid activation function. And in general, what an activation function is going back to the mathematical model of neurons in the brain. You have neurons which are connected to other neurons via synapses, and synapses essentially have a kind of weight. That's where the idea of weighted edges comes from. And then the input neurons would effectively have some kind of signal, and the weights of the synapses would be multiplied with those signals, and you have a weighted sum, and that produces some kind of activation. And the activation function in this mathematical model of a neuron would be modeling the rate at which the neuron itself would fire given these inputs. And firing means sending off its own signal. And so that's what activation functions do. They also have other purposes. For example, in our case of the discriminator, this particular activation function has a nice property of mapping functions into a range of 0 and 1, which we can then interpret as probabilities. So that's what we also need. But I just want to actually use this as an example of a kernel. And there's two things you need for the implementation of a kernel. The first is a forward pass, which is actually just the definition of the kernel. And in this case, the sigmoid is usually denoted as sigma, and the input is usually z. And so sigma of z would be, this is the definition of the function, is simply 1 over 1 plus e to the minus z. And then what we also need for a kernel is a backward pass. A backward pass is the derivative, and we need this for the optimization process. So for the sigmoid, in this case, it's actually quite convenient. The derivative is defined in terms of the function itself. So it's the sigmoid at z times 1 minus the sigmoid at z. And in this case, I can actually very quickly give you a look into, this looks small, what a kernel would look like. This is Eigen. Eigen is a matrix manipulation library that's used by TensorFlow. And I just want to give you a very quick look at what a forward pass of a kernel would look like. We'll look at a lot more code later on. So here is the scalar sigmoid op, and this is what TensorFlow, for example, uses for the sigmoid operation. It's very simple. It's 1 over 1 plus e to the minus x. And if we want to look at the backward pass, this is now in TensorFlow itself, just again to give you a taste. Usually for the optimization, we need to define the chain rule, which multiplies two derivatives. So the output gradient would be one of the derivatives, and here is the one we're calculating ourselves, which is sigma at z times 1 minus sigma at z. So this is a taste of the forward and backward pass of a kernel. I want to talk about something very important at this point, which is actually one of the most important aspects and maybe secrets of machine learning engineering altogether, and that is quantization. So for this, I want to first tell you that, in various kinds of machine learning models, one of our goals is to create robust architectures. And that means, for example, if you're creating an image classifier for species of cats, then for a particular species, you can't always expect to have perfect images, right? So on some images, you'll have different lighting behaviors, you'll have different objects in the foreground and background. Sometimes the cats will look friendly, or that's probably not the case. Sometimes they'll look like they hate you, sometimes they'll look like they hate you a lot. So generally, you want your machine learning models to be robust against variations of the input, robust against noise. And now we can do a kind of thought experiment. If you think of a 64-bit floating point value with 20 significant digits, imagine we're modeling some kind of noise, which is simply additive white noise, so it's a random value that's added to that floating point value. And imagine now that the noise just so happens to be the negative of the last 15 digits of that floating point value. Then the result of that is the same floating point value, but with only 5 significant digits. But so if our machine learning model is robust against noise, this means that the output should still be the same. And in turn, that means that if that is the case, we can simply always use reduced floating point precision for all of our floating point values in our machine learning model. And so quantization actually happens to be, or has turned out to be, one of the most important factors of machine learning hardware and machine learning frameworks at all. And so the way quantization works in some cases is that we can even go from 64 bits down to 8 bits. And what this means is that we can use 8 times less memory, and if you have 130 million floating point values, dividing that by 8 is a huge thing. And it also means we can send more things across the network. And it also means, of course, that doing math with 8-bit floating point values is a lot faster than with 64-bit floating point values. And the way quantization could work, for example, is that if you have the sigmoid here, we know that the sigmoid has an output range of 0 and 1, which means that we can add a kind of quantized op to our computation graph, which will simply linearly quantize that value, that 64-bit floating point value, into a single 8-bit character or chart. which would, for example, map the value of 0.25 to 64 and values between 0 and 64, 0 and 0.25 to some value in between. And now we have a 8-bit carrier which we can send to some hardware accelerator which knows how to, for example, do matrix multiplication with these quantized floating point values. And those are really fast. And for example, if you're interested, there's this library called GemLoP. So Gem stands for General Matrix to Matrix Multiply, which can actually operate on these low precision floating point values really efficiently. Right. Now moving on to the lowest layer of our stack, which is hardware. I want to give a general idea of the kind of hardware we use in machine learning. There's three basic kinds, or three kinds of processor architectures. The first two are kind of obvious. The first one is CPU, and I want to kind of make a metaphor with fish. So we all know that CPUs are kind of very strong processors. We usually have few of them, just as there are usually very few sharks. I mean, I've hopefully never encountered them, but there's usually very few of them. But they're very strong. They're very general. They can do lots of things. And in contrast, GPUs would be more like a swarm or a school of piranhas, where each individual processor itself is not very powerful, but in their masses, they're still extremely powerful. And it has actually turned out that GPUs are one of the core factors of why I'm even up here talking about deep learning, probably why you even know about deep learning. So GPUs have been the most important hardware innovation for machine learning in recent years. And the reason why is that, well, what GPUs are really good at is doing lots and lots of small computations for each pixel of your screen. And as you saw earlier, for neural networks, we often have to do lots and lots of small operations for very many small units, small neurons. And that's why GPUs are actually just really, really well suited to neural network computation. And I'll show some examples of GPUs later on. And the last kind of processor are ASICs, which are weird. So the thing about ASICs, or application-specific integrated circuits, is that they're really, really good at one thing usually. And that thing is, for machine learning, often matrix multiplication. So they're really good at one thing. They're not very general. They can't do everything like a CPU, or they're even less general than a single GPU core. But they're really, really good at the one thing that they do. And that's ASICs, and I'll give an example of them in a bit. All right, now we're moving back up the stack, and now I'm going to show more practical aspects of machine learning. All right, so here's an example of a GPU, and I want to give some typical examples of machine learning devices. So this is a Titan X from NVIDIA, and this is the kind of GPU you would often find in machine learning labs. So this is we have 4 of these in my lab, and they are reasonably cheap. They cost between $1,000 and $2,000, and they can nevertheless speed up your computation by a large factor. So to give you an idea, training on a particular data set called ImageNet, which has around 1.5 million images, on an Intel Xeon Phi takes around 43 days, and on this Titan X takes 6 days. So that is quite a reasonable difference, and of course there's lots of optimizations afterwards. Just a few weeks ago, Facebook AI Research released a paper on training on the same data set in 1 hour on 256 GPUs. So we're definitely making progress in this area. Nevertheless, this is a good example of a GPU. It has 3,840 cores, and because it's CUDA cores, each of those run 32 threads. And it has 12 gigabytes of on-chip memory. And I also want to maybe quickly clarify what GPUs have little of, because I think that's maybe sometimes unclear. What GPUs have little of is, first of all, memory, on-chip memory. So if you have a strong CPU node, you'd have something between 64 and 128 gigs of RAM. So strong GPU nodes would only have 12 gigs of RAM. And what they also have little of is bandwidth on the PCI Express between the CPU and the GPU. But the one thing they do have very much of, and which is something sometimes unclear, is bandwidth on the chip itself. So the Intel Xeon Phi, which is Intel's kind of flagship parallel processor, has around 200 gigs per second bandwidth. So this GPU has more than twice that. So they do have very high bandwidth. And the other thing they have a lot of is flops. So this Titan X can do 12 teraflops. The Intel Xeon Phi, I believe, can do around 2. Right. Another example here I want to give is of a typical machine learning server. This one is called Big Basin. It's designed and deployed by Facebook, but it's actually part of the Open Compute project, which means it's open source. It doesn't quite mean you can git clone the server and it will just appear in front of you, but you can git clone the plans and build it in your garage. And it has 8 NVIDIA Tesla P100 GPUs, which gives it about 10.6 teraflops per GPU. It also has 16 gigs of RAM and has NVLinks between the GPUs, which are faster than PCI Express. And they also have support for 16-bit floats, which, as I mentioned, quantization and reduced floating point precision is one of the most important factors for machine learning hardware. So that's a typical server. Now, this is a typical, or one of many ASICs for machine learning. It's called the TPU, the Tensor Processing Unit from Google. And some things I'm going to say here are not quite right because Google just released TPU2, but they also didn't release the specs for it yet, so I can't be more right than I am. But the original TPU released last year was a coprocessor. That's why I highlighted, because it's not a general piece of compute like a GPU or a CPU. It's a coprocessor. You attach it to another device. And that also means that it only has 24 megabytes of on-chip memory. But the one thing it's really good at is computation of matrix multiplications. And you can see for these 8-bit quantized operations, it can do 92 teraops, which if you compare that to the equivalent Titan X is very little, is a lot more. And also for, so those are teraops for 8-bit ins, and even for flops, it can do 42 flops compared to 12 teraflops. So that's a typical ASIC, and there's lots of other devices, lots of startups coming up with exciting new architectures to solve this entirely new way of computing. So I mean, neural networks are really extremely parallel. GPUs are really parallel, but we need even more parallel hardware. So there's, as for example, a startup called GraphCore from Bristol in the UK, which is developing a new kind of architecture with 1,000 cores and a very different kind of computing architecture. So we're no longer talking for Neumann or Harvard, we're talking a completely new way of computing. All right, now I'm going to show code in a bit. First of all, on the kernel layer, there's two very important libraries that lots of frameworks like TensorFlow or Caffe or other frameworks use to implement their operations. And those are cuDNN and Intel MKL. So cuDNN is from NVIDIA, and it's a very low-level primitive library for, in case of cuDNN, for things like convolutions or activation functions or other kinds of neural network layers. And in the case of cuBLAS, for things like matrix multiplications. And on the other side, you have Intel MKL, which is quite general. So who here has used MKL before? All right, so quite a few people who probably maybe have not done it for neural networks, but just for general linear algebra or other purposes. So these two libraries are used by frameworks like TensorFlow or other frameworks to do their low-level grunt work. And at this point, I'm going to switch over and show you the implementation of a convolution with cuDNN. All right. Is that big enough? All right. So let's look at some code, and we can actually run it afterwards. So this here, first of all, it's just code to load and save an image with OpenCV, so I'm just going to skip that. The one thing I want to say is that both cuDNN and MKL, these are C/C++ libraries. And we all know that when it says C/C++, it's going to be really bad, and it's going to involve a lot of pointers. So it's a C/C++ library, but it's not really a bad thing because these are supposed to be low-level libraries wrapped by other frameworks. So they don't really need to have a very pretty user interface. They just have to be portable, essentially. And also because it's C, it can be wrapped to other libraries or other languages like Python or Ruby or whatever. So the way cuDNN works is that it has descriptors for the various operands to its operations. So here we have, for example, a tensor descriptor. So first of all, a tensor is simply a multidimensional array. So for example, an image would be a 3D image would be a 3D tensor, and if we stack multiple of those 3D tensors together, we get a 4D tensor, and so on. And so cuDNN operates with those tensors. And what we need for a tensor essentially is to describe the way it's laid out in memory. So in this case, for example, we would say that it has how many rows it has, how many columns it has, how many channels it has, and also because cuDNN usually operates on batches, we can also say how many images we have in a single tensor. And what we also specify here is the layout. And that's actually one of the great things about cuDNN is because different frameworks like TensorFlow or other frameworks will have different ways in which they like to lay out their tensors in memory. And cuDNN has quite a lot of support for different kinds of layouts. So for example, in this case, the n would be the images, then we would have the height and the width, and then finally we would have the channels, whereas other libraries might like to prefer this one down here, which is first the images, and then the channels, and then the height and the width. So switching that around. So cuDNN has support for that. In this case, we would define a descriptor for the input. and then another descriptor for the kernel, which we convolve the image with. So the input is the image. And then we have another descriptor for the convolution algorithm that we use. In this case, we're specifying a few things. We're specifying the amount of zero padding we add around the image. We specify what the stride is, so the amount by which we slide the kernel across the image, the convolution algorithm, and also the data type of the convolution. Then skipping down a bit here, what's also interesting at this point is that we can specify different kind of convolution algorithms. So usually you want to specify this, fastest, but you might also want to specify one that uses lower memory, or also you might have an explicit choice. So for example, you can pass Cudier and convolution forward algo explicit gem, and that would actually use the algorithm that I described earlier, where you actually explicitly model the convolution as a matrix multiplication. The problem with that, I also outlined that earlier, is that you have lots of copies of data between individual patches of the image. So the implicit version would be a bit more smart about that and how it does the actual operation. Nevertheless, here the workspace is something that Cudier uses to know how much memory it needs for its operations. And the actual kernel that we're using is this one here. And this is essentially along the same lines as the kernel I showed earlier for the edges. So on a single color patch, this will still be 0 because it'll all be the same color. But on edges, it'll be a non-zero value, and you'll see that in a bit. The actual convolution itself happens down here, so you can see all the good stuff, the actual mallocs. We know it's C/C++. But here's the actual convolution operation. Because it's C, the functions take 1,000,000 parameters, of course. But the actual convolution happens here. Then we copy it to the output. We're using CUDA memcopy. So this is CUDA, by the way. I put all my code open source, but this won't run on your CPU if you don't have an NVIDIA GPU. But then we save the image. And now I'm going to switch over here. And I can log into my lab cluster. All right, here is all the stuff. Okay, I already made it earlier. Anyway, we can use this code to apply convolution using CppCon logo. This looks like this. So that's the image that we're convolving down there. And now we can apply the convolution operation. It's actually happening. We can copy over the image, and that should open up. Right, and so I mentioned this was an edge detection kernel. And as you can see, using that particular kernel for the convolution, we picked up exactly the edges of the image. And so in a neural network, you would hope that the optimization process would lead to the neural network actually learning this kernel on its own and pick up these edges and then do more interesting stuff with it. So that was a convolution with cuDNN. I have an equivalent version using MKL in my repo that you can check out yourself later on if you want to. So that was that. I think how much time do we have left? More than enough. All right, so another sample I want to give is actually implementing your own kernel for TensorFlow. That's the next sample. So let's look at that. All right, so TensorFlow, I'll talk about more about it in a bit, but it's essentially one of the biggest deep learning libraries. I'm going to show you how you would implement your own kernel for it. So we're going to implement the sigmoid operation, which I talked about earlier, just that we're going to call it CppCon sigmoid, so it's far superior, of course. So essentially, it boils down to very little code. So that's the entire file. You register an operation that we call CppCon sigmoid, and you specify the types that you want to use it for, float and double. So TensorFlow has its own type system, and you describe the input and the output. This thing here just checks that the output shape is equal to the input shape. And then down here is the actual magic. It's very little. And as I mentioned earlier, TensorFlow uses Eigen, so you'll be dealing a lot with Eigen, which is a very nice library for matrix manipulation in general. And down here, we perform this operation that I mentioned earlier. It's 1 over 1 plus e to the minus z. And the nice thing about Eigen is that you can use tensors and matrices just as if they were single values. So this means that if we do minus input, so input is an entire matrix, that will do an element-wise negation, and doing that dot x will do an element-wise exponentiation, and 1 plus that will do element-wise addition of 1. And then we do dot inverse, which computes the inverse of that. And that is the final output value. And now we can try that out. Close this. Is this big enough? Yeah, probably. All right, so let's go up here. Where am I? All right, so I'm making it. I'm just actually compiling exactly this file with a make. And now we can go into TensorFlow, or actually into Python. So this is not Python. This is C++ 49. It just looks very much like Python. We've made a lot of progress since then. So first of all, I just want to very quickly show you this, demonstrate you this idea of static graphs, what that actually means. So if I define a constant with TensorFlow like this A thing is not actually a value, it's just an operation that is a handle to that value. So it represents the computation graph leading to that value. And if I define B and then C as A plus B, C is not a value, it's just an operation representing this computation graph. And then you usually have to do something like define a session, that's what TensorFlow calls it. And then you can pass to the run method of that session your tensor, or your computation graph, and it would map it to devices, map it to multiple machines if you have multiple machines, but ultimately produce the actual output value. So that's what static graph means. In our case, we're more interested in actually loading our own kernel, which we got. We do this with tf.load_op_kernel. So we compile our kernel into a shared library, and then TensorFlow is a nice mechanism for just loading that into its framework. So we can load that, and we can get it. Let's just call it m dot, I think it should be here. So this is the kernel, this is the thing we defined. And now we can actually just run that. Let me do s dot. So this is the function that we have, and we can pass it something like 0.5. And if this works, then as you remember maybe earlier, the sigmoid at 0, it's equal to 0.5. So if it works, it should hopefully be equal to 0.5. Now we need to create a new session to evaluate it. OK, it worked. So as you can see, with just like around 50 lines of code, we added a kernel to TensorFlow. The one thing that we aren't doing here, which I mentioned earlier, is defining the backward pass, which creates the derivative. The reason why is that most of the derivatives in TensorFlow are actually defined in Python, and I'll talk about that more later, but that's actually one of the flaws, or not flaws, but one of the problems with TensorFlow that other libraries solve in a better way. OK, so the one thing that I didn't want this talk to be exclusively is a comparison of frameworks. Nevertheless, I do want to very briefly give you an idea of the different kinds of frameworks we have in the deep learning space. The first one is TensorFlow. You've probably already heard about it. And you'll see that most of these frameworks have some kind of corporate name attached to it, whether you like it or not. So this is TensorFlow. It was released by Google in 2015, so quite recently. It uses a static graph model, which you just saw. So you're not actually computing anything yet. You're just defining a graph in a declarative way and passing that on to your machines and then evaluating the graph. And it has support for GPUs. It can distribute your model automatically for you, which is quite nice. It does not have a very stable C++ API. And the reason why is that, well, a lot in TensorFlow is actually defined in Python. And for example, the derivatives, so lots of the backward passes are defined in Python. And that is actually something that the TensorFlow team is currently trying to solve. So they're kind of working backwards now because they define so much in Python, but notice that people actually want to, for example, wrap TensorFlow in other languages or just programming from C++ themselves. They're now kind of working backwards to move more into plain C or into C++, and so that they can have more APIs built based on top of that. But it's actually, so the one thing that's nice about TensorFlow is that it's like batteries and Lunchbox included. So you can simply define your model, it will distribute it automatically for you. There's also parts inside TensorFlow to, for example, create a REST API for your model or help you with your training data. So there's lots and lots of stuff inside the library. The one thing that so I use TensorFlow myself, but the one thing I don't like about it is that it's solo level. So you really define these basic additions and multiplications. And it's solo level that there's around 10 different competing higher level libraries based on top of TensorFlow that all define the same like dense layer, all the same convolution. And so what can happen is that you read 10 different papers and look at the code for all of those papers, and each of those implementations will use a different higher level library on top of TensorFlow. So that can be quite annoying. The other two I want to talk about are PyTorch and Caffe, and I put them on the same slide because they're kind of complementary. So they're both developed by Facebook. And Facebook took a bit of a different approach. They kind of actually split the responsibilities between research and deployment. So PyTorch on the left uses dynamic graphs. And I'll tell you that dynamic graphs are actually a lot nicer to work with from a research perspective, because you can actually use Python's or C++ or whatever, Python's native control flow. You can actually use if clauses and actual while loops. And that makes a huge difference, especially in terms of debuggability, because your while loop is not in a graph somewhere on a distant device. So that makes a big difference. At the same time, it's still very fast. So the one thing that's good about static graphs usually is that you can actually do things like compile them. For example, if you have the operation x times x, then in a computation graph, you can imagine this as having an input x and the output x squared, and then two edges going from x to x squared. And then you could run a compiler which would, for example, fuse those two edges into a single x squared operation, which means you only have to transfer the data once to that operation. And because it's defined, the graph is defined ahead of time, you can do things like optimizations and compilation. But you can't do that with dynamic graphs, but in this case, PyTorch is still very fast. But it's in pure Python. On the other side, then you have Caffe2, which is based on Caffe, which first highlighted actually has a C++ API that's quite usable, not very usable, but it exists. And the idea is usually that you would do your research in PyTorch and then export your code into a format understood by Caffe2. And Caffe2 uses static graphs and then can do things like compilation and optimization and distribute your model across many machines. But it's a lot less nice to work with, but you have this split of responsibilities, which is nice. The last framework I want to talk about is MXNet. MXNet used to be a community-driven project, so not affiliated with any company, but then Amazon thought it would need a deep learning framework too, and it was a lot easier to take this one than to argue with Google about accepting pull requests. So MXNet is now developed by Amazon, which is actually great because it's a great framework and Amazon puts a lot of effort into making it even better. And it's actually going into Apache right now, so very soon it will be Apache MXNet. Right now it's just MXNet. And the one thing that I like very much about MXNet is that it's actually very modular. So for example, they've abstracted the entire scheduling engine outside of the framework into a separate library that you could use for other kind of HPC scheduling problems, for example. So it's very modular, which is nice. And it also has the only really nice C++ API with which you could actually define a proper model yourself. And I think we actually have time to show you how that would look like. So let's look at that. We're going to define a very simple machine learning model. Actually, it's not simple. I'm not going to go into very much detail with it, but I just want to show you that MXNet has actually a very usable research API in C++. So this is C++, as we all love it. And we're defining a static graph with MXNet using C++. So as you can see, MXNet has these symbols. A symbol is a node in the computation graph. And we can simply use a reasonably nice user-facing API to, for example, do a convolution. And the convolution would be a computation graph node itself. And we're passing that through these functions to create a neural network. In this case, this is an image classifier. But we can use, it has a very nice API. That's what I'm trying to show. At the bottom here, down here, I can show you how to actually train it, which is also very straightforward. So it's not very much code. Here we're defining the nodes of a computation graph. Here I'm initializing them with a value sampled from a normal distribution, and the actual training itself happens down here where we're just calling .forward, which does the forward passes on the kernels, and .backward, which does the backward passes on the kernels. And that's essentially it. It's around 250 lines of code to create a full-fledged neural network using this pretty nice C++ API. And now we can do something here. Let's go up. Okay, so we can try this out. I think I need to remake this. Okay, I have some environment variables here. This should hopefully be fast. Okay, this is actually going to train it live. This is going to take 6 days, so I'll see you back next week. No, it just takes around a minute. But I'm still going to move on. I think this is actually the last part. So we can actually just start taking questions now, and this should be finished in a minute or two, and then I'll show you a demo of using a real neural network in C++. All right, so any questions?
Hi, you showed performance with NVIDIA's Pascal GPU. Have you tried running with Volta architecture, and did you get any performance improvements?
No, I have not run it with Volta. I mean, getting access to GPUs at all is a nice thing, and I don't have that modern hardware in our lab. But I imagine it's a lot more efficient using those more modern GPUs. I mean, NVIDIA has also a lot better hardware than the one I showed. It was just more an example of a typical GPU you would find in the lab, but I have not used the Volta.
Yeah, I'm very interested how it compares with the Google stuff, and I've seen like impressive numbers. So I want to know if it actually performs that well in, for a real use case. But
right.
Sometime later. Okay, thank you.
All right. Yes.
So you said you can reduce your precision of the variables to 8-bit because it doesn't really matter because the neural net is supposed to be robust against fluctuations.
Yeah.
But there must be some trade-off because you can't reduce it to like 1-bit, right? So what is the trade-off that you're doing at this point?
Well, I mean, you're not getting the same accuracy for sure. And what's also important to know is that the training itself would still happen with 64-bit floats. But once the model is trained, once it's robust against noise, you can use reduced floating point precision. You can't scale it to 1-bit. Actually, there are neural networks that use a single bit, and they work quite well. But the trade-off you're making is accuracy. So with 8-bit floats, you might not get 99%, you might get 97%. So you'll have reduced accuracy because you'll have reduced precision. But the point is that you have so much more performance that it's actually a good trade-off.
Thank you.
Yes. All right, so if anyone's still around, this is now trained, and I made a cute app. So anyone with half a mind would actually tell you that doing a live demo with a stochastic program is the worst idea ever. But I'll risk my neck to see if this classifier that I showed you actually works. So this is a handwritten digit classifier, and if this works, then maybe this will, yes, actually do something. So the code I showed you with around 250 lines of code actually trained a very nice, cute little neural network that predicts the digit that I'm drawing here reasonably well, I believe. At least 50% of the time, it works every time. All right, yeah, that's it for my talk.
So my question is, you showed a lot of neural network frameworks. Are there any other sort of general classifier frameworks for learning models, like such as SVM or Bayesian networks, stuff like that?
You mean more like higher level networks, or you mean for more general machine learning?
I mean, like in C++, for example, are there other frameworks that you're aware of that can do these other kind of learning?
But do you mean higher level tasks, or do you mean other kind of machine learning except for neural networks?
Other machine learning, sorry.
Yeah, there's one called DLib. DLib is quite old and it's quite mature, and it's been used for a long time for other things like SVMs or other kinds of machine learning models. They have some pretty nice neural network APIs as well, but it's very useful for a lot older and more mature stuff. Yeah.
Thanks.
Sure.
So what would you say is the main benefit of doing deep learning with C++ compared to Python? Does it train any faster or predict any faster?
No, there's actually, the only reason why you would want to actually define your model in C++ is because you have a pure C++ code base. If it's possible, the much smarter way of doing it is to use Python, which is just a lot faster to iterate with, and then train your model and then export it and load it in C++ using, for example, the TensorFlow API, which has a very sweet API to just load a trained model, and then you can integrate that into your code, your C++ service, and just use predictions from C++. So that's actually the better way. But sometimes you just might prefer C++ for fun, or sometimes you don't have a choice of using an external code. Yeah.
Thank you.
Coming back to that resolution question, is it possible to do a couple, like the bulk of the training path is with low resolution, and then at the end just continue training with a higher resolution?
So you mean like once it's like sort of good, stop doing that precision? You could probably do that. People have generally found that doing the reduced precision during training is not a good idea.
Okay.
But at the same time, I think, yeah, I mean, doing reduced precision would probably reduce the training time, but I imagine the idea is that if it takes 2 weeks to train, then it's trained and you're done, and then afterwards the performance really counts once you run your service. Okay. But that might be an interesting idea, yeah. Looks like we're done. Cool. Thanks.